All right. So also, if the slides doesn't move, you tell me immediately. Today, so far we have studied two kinds of model. One is an simple distribution model. You have a set of variables x, and you have some observations. We assume some priors, and you estimate the posterior distribution and its parameters. The second is we have a conditional model where we have two types of variable, not one type. You have an input variable x and output variable y. And rather than the joint distribution between xi and y, we are more interested in the conditional distribution y given x. And what we have is for the training set, we have both x and y values available. But for the test set, we have only the x values available. Y values are to be predicted along with the uncertainty in prediction. We studied some type of conditional models, for example, the linear regression model, the logistic regression model, the Gaussian process model. So these are all examples of conditional models in the sense that we are interested in E, Y given X. Next, we study the third type of models where we not just have X and Y, we have an additional variable z, which is a hidden or a latent variable. So this can be happening for both the distribution model as well as the conditional model. So you may have x, y, and z, or you may have just x and z. If you are modeling distribution, you can have x and z, and if you are modeling conditional models, you can have x, y, and z. The thing is that this z is the extra, and there is some this z is called a latent variable, and there are some advantages if we introduce this latent variable. In this plot diagram, you can think of it like this, that you have this x, you have a set of observations x1 to xn, which are observed, and there is a latent variable zn, which is kind of not observed. Okay, not observed both during training and testing, neither during training nor during testing. And then when you model the distribution of xn, you have some kind of maybe prior or other parameters, which is a theta. Similarly, zn can also have a set of distribution parameters, which we call phi. So theta is a parameter for xn, phi is a parameter for zn. But zn is a latent variable which determines x, but zn is not observable. We don't have the values of zn either in the training set or in the test set. We could further have a conditional model. We could further have a y, which again depends on x. But for the moment, I am not doing that. In fact, the result without y, they smoothly extend to the conditional models also. So what is the advantage of this latent variable model? The advantage is often you can think of Zn as an augmentation of the variables, as a variable augmentation. You introduce additional variables in addition to x. Often this simplifies the entire inference process. We will soon see an example. I mean, it may appear a bit counterintuitive. We are introducing more variables. Why should it simplify? But we'll soon see that it may sometimes simplify the model. One example we have already seen. For example, in the logistic regression, we introduced the output of the logistic sigmoid function. Input is x. Output, instead of directly taking the output, we construct another variable, which is the sigmoid of x, which we can consider as a logistic regression, the output of the logistic regression. Note that this output of the sigmoid is not really observed variable. We actually observed x. That output of sigmoid we are constructing using the sigmoid function. But it is helping us. Why it is helping us? Because if we are doing a classification problem, this sigmoid output would really give 0, 1 values. So that will give us some nice classification outputs. So this is an example where model augmentation simplifies the inference procedure. We'll see more examples. Another advantage is that sometimes there are some properties of the data or features of the data which are latent, which are kind of non-measurable or unobserved. For example, the topic of a document, or for example, non-observable in the sense that they are not directly sensed or observed. Say the cluster belongingness of a set of data, or maybe an embedding and vector representation. You all now work with this embedding. So you have a embedding is kind of a low dimensional representation of a data point. So all these are kind of latent features. They are not directly observed, but they are more useful than the directly observed features. So this is another motivation for which this latent variable analysis is performed. Let me quickly explain these two cases. The first case where introducing additional variables helps you in simplifying the inference, probabilistic inference procedure. Let us take the following problem. So you are doing a team selection for a sports meet, say inter-IIT or something, sports meet. And what we'll do, we'll do some trial and ask the students to participate in the trial, and some trainer or somebody in the trial, based on the performance, will give some score, 0 to 100. What I want to do is I want to sort of predict the performance score from historical data. That means previously people have performed with some parameters, and we know their parameters, and they have obtained a score, and based on that, say regression or something, will predict the score. Okay, and let's say these input parameters are kind of height x1, weight x2. Now say the number of calories, tell you how active the person is, maybe x3, and the hours of sleep, let's say hypothetical x4. So x1, x3, x3, x4, and we want to predict the output. So the situation we can think of like this: you have 4 variables denoted by these nodes x1, x2, x3, x4, and you have to sort of, without actually doing the trial, because kind of we are doing a screening. I mean, we don't want everybody to come to the ground and do a trial. We, based on this x1, x2, x3, x4, we want to screen them and predict their score, and only those with a high score will come and actually give the trial. So we are sort of interested in the probability score given x1, x2, x3, x4. So x1 determines score, x2 determines score, all of these determine the score. And additionally, if you look at the parameters, they have an interrelation between them. They have a correlation between them. So really, this x1, x3, among themselves, they are also highly correlated or interrelated. So if you want to really do this prediction a probabilistic way, we have to estimate this conditional probability along with given all these variables, and the all possible combinations of x2, x1, x2, x3, x4 would be rather large. So in order to calculate the score, you actually need a lot of data. You'd actually need all combinations of somebody who is height is this, weight is this, how much he has slept, how much he exercises. So all different combinations, numerous possibilities are there. And you may not have data for all those possibilities. So if everything interacts with everything, then you really need large amount of data to properly. Otherwise, what we'll have, there will be a lot of students who have some combination of these variables in which no data is there. So if you remember our previous regression example, we'll have a lot of uncertainty about the score. We are not really sure about the score. So we have to call them and actually perform. So we're not really sure because we don't have data. Okay, we don't have data. it is a difficult inference problem. You need a lot of data, even just with 4 variables. Now, what we do, we kind of, based on our knowledge of the problem, introduce an 5th variable, which is kind of abstract kind of thing, or hypothetical variable, which we call fitness. It's kind of, not a real variable. It cannot be measured actually. So it's a hypothetical variable, which we believe or know or something. And your fitness level is directly determines your score. Your score will be determined by your fitness level. And in turn, fitness level would be determined by your height, by your weight, by your BMI kind of thing, and your hours of sleep kind of thing. So all these variables would in turn determine this, and this in turn would determine this. So you see, just the introduction of this 5th variable has removed all these edges in the network. And this is, I'm writing down these values. This is not really a model. So what I would rather do is that I'll build, instead of one big model of 5 variables, I'll build 5 small models. So one model, how does X1 determine fitness? Another small model, how does X2 determine fitness? X3 determine fitness, and X4 determine fitness. These 4 small models will build, and we'll build a 5th small model. How does fitness determine score? I mean, I'm not really doing the exercise. It can be shown that the 5 variable models is the number of possible combinations, or the size of the table, all possible combination, is much larger than these 5 small models taken together. So this is just a small model, this is another small model, this is another small model, small possible variations in X1. Okay, so these are much smaller model, and so what we are actually doing is we are doing a divide and conquer policy. We are breaking down a bigger problem into a number of smaller problems, which are easier to solve, and then putting them together. So this is what, and the number of model parameters, you can imagine. So if I imagine a 4-dimensional Gaussian here, the covariance matrix would be 4 by 4, 16 entries. But here we have 2 by 2 Gaussians, X1 against fitness. So I have 4 2 by 2 Gaussians. Okay, so or rather, if you take 5 model here, it is a 5 by 5, 25. It is 4 2 by 2 and 5th 2 by 2. So 20 parameters you need, 20 covariance values you need. Right. So this is just for variables. That's why the gain is not so much. For a larger number of variables, the gain would be much more. So this is the usefulness of this latent variable model. We have incorporated our domain knowledge with the help of this, and it has helped reduce our model parameters on size of the model by divide and conquer strategy. Okay, so this is just illustration of one of the examples. So one question that might arise, that why not take this as a parameter? Why you are considering it as a variable? You can consider it as a parameter of the score function, or of the joint distribution of the score function. We can have this fitness as a parameter, and have several, say, Gaussian, where this fitness is one of the Gaussian parameter. It turns out that there is a thin line between what is a parameter and what is a latent variable, because parameters are also unobservable, they are estimated. Okay, there is a thin line. What is a parameter? What is a latent variable? The rule is that these parameters, say the mu and the sigma values, they govern all the data points. So if we assume a Gaussian, any data point following that Gaussian will have this mean and this variance. So the parameters kind of are parameters for all the data points, whereas the latent variables are specific to a single. For example, we talk about fitness of a single person, we talk about fitness of a single row. Whereas if we fit a Gaussian to this entire data, the mu value is the mu value for all the examples. Okay, so latent variables are kind of local or specific to an example, whereas parameters are global. Okay, so this gives us an advantage in reducing the inferencing complexity also. We have seen before that if we do a full posterior distribution with a lot of parameters, then the expression for the distribution becomes full posterior distribution, full probability distribution becomes difficult. Sometimes what we do, instead of a full Bayesian estimate, we have a point estimate, a MLE or a map. But that doesn't give up the summary. And so what we can do is that we can kind of do a mixed inference. We do a full posterior, full Bayesian posterior for the local. See, both have to be estimated. You have to see, if you look at from the estimation point of view, X is what you have observed. Everything else you have to estimate. The parameters theta you have to estimate. The latent variables Z you have to estimate. Only difference is that Z you have to estimate for every instance, and the parameters theta you have to estimate for all the instances. Same parameter. Okay, so this might be a difficult task. So often what we do a trade-off. We do a point estimate, say MLE or map for the parameters. We do a single point estimate. We are not really interested in the distribution of theta. We are interested in single value of theta. Whereas we do a full posterior estimate for the Z values, the latent variables, or the local variables. Then for them, we are interested in the distribution. So this reduces the complexity. This is called a hybrid inference technique. We'll soon see an example of this hybrid inference technique and how this introduction. So the latent variable reduces the load of full posterior estimation for both parameters and latent variables. It does full posterior only for the latent variables, and it allows you to do a point estimate for the parameter variables, reducing the complexity. We'll soon see an example of this. Okay. So the example, another example of where latent variable is useful, introduction of latent variable is useful, is something called a Gaussian mixer model. So you remember earlier what we do? We got some data and we just wanted to know what the we assumed that this data comes from distribution, say beta or a Bernoulli or a Gaussian, and we are interested in estimating the parameters of the Gaussian or the Bernoulli from the data, and with some probability, we get the posterior. Suppose we take a bivariate case and our data is distributed like this. Our training set is this kind of thing. If you want to fit a bivariate Gaussian, a single bivariate Gaussian, it would rather be a poor fit. It would rather be a poor fit. It will just try to fit a big circle or ellipse, something like this. And in fact, this is not the right fit. The right fit would some ellipse like this. Anyway, so there would be a lot of places where the distribution would say a high probability value, but actually there are no data points there. So it is not a good fit. Instead, if we fit 3 Gaussians, one like this, one like this, and one like this. So all the points that belong to Gaussian 1 is red, green, and for Gaussian 2, and blue for Gaussian 3. This is a better model. This is a better fit. And this is called a Gaussian mixture model, GMM. It's a mixture of Gaussians. So let us see what it really means. It means that your data X, the distribution of X, is a sum of k number of Gaussians. In this case, k equal to 3. K number of Gaussians or rather k number of component Gaussians. So there are k components of the distribution. Each of the components are a Gaussian. So we have, let's say in our case, the first Gaussian will be mu1 sigma 1, second Gaussian would be mu2 sigma 2. Mu1 is something here and sigma 1 is something like this. Mu2 is somewhere here, something like this. So you have three Gaussians, and then we have a mixing coefficient known as pi 1, pi 2, pi 3. So it's kind of the weight of each of the Gaussian for a particular weight of each of the Gaussians, right? It's called the mixing coefficient. And your data distribution X, so given a point X, you first find the probability that is given by mu1 sigma 1. Let's say I call it N1, given by N1, the first Gaussian, weighted by pi 1. Pi 1 is the mixing coefficient for the first Gaussian, or you can think of it as weight of the first Gaussian. Mu pi 2 sigma N2, the second Gaussian, pi 3 N3. So say, let's say a point falls here, its probability according to the first Gaussian will be very high. According to the second Gaussian will be low. According to the third Gaussian will be low. If a point falls here, its probability according to the first Gaussian will be high or moderately high. According to the second Gaussian will also be moderately high. According to the third Gaussian, 0. So the probability of this point would be this probability weighted by pi 1 plus this probability weighted by pi 2, and maybe a small from here weighted by pi 3. So we add up these three probabilities with some weights, and you get the probability of that point. So all three Gaussians contribute by varying degree depending on where the point lies. Okay, so this sigma pi k n x mu k sigma k, because we are adding up, we are doing a weighted sum. This is called a mixture, and since individual components are Gaussian, this is called a Gaussian mixture model. The final distribution in this case, we plot in z-axis, may look something like this. Okay, so it's kind of multimodal. There are several peaks in the distribution. But if this px has to be a probability distribution, some properties of this pi k have to be followed. Pi k has to be greater than or equal to 0 for all k, and some of the pi k values, some of the weight values over all the Gaussians has to be 1. They add up to 1. Okay, so it's that is what. Otherwise, you will for every, if you take the area under the curve, you know, for a distribution, finally, if you integrate px from over the entire space, this has to be 1. So that comes only when sum of pi 1 plus pi 2 plus pi 3 equal to 1. It can be shown that if you have any arbitrary distribution, any whatever complex distribution, you can have a GMM with suitable number of components, suitable value of capital K to approximate the distribution, the density of the distribution. You can approximate. Only thing is that the more complex the distribution becomes, more and more components you need. Okay, but it is a universal approximation. You can approximate any distribution using GMM. Okay, so now our problem is the following. Given a set of capital N number of data points, x1 to x capital N, you have to estimate the parameters of the Gaussian. What we do, we assume the value of capital K. We assume that there are 3 Gaussians or 5 Gaussians or 7 Gaussians or 6 Gaussians. We assume them. We assume the number of components, and after that is a hyperparameter. After assuming that hyperparameter, we have to estimate pi 1 mu 1 sigma 1, pi 2 mu 2 sigma 2, pi k mu k sigma k. These are the parameters of the GMM. These we have to estimate from the data. Okay, so let us see how we'll estimate this from the data. Okay, and also let me tell you one thing. For the moment, we'll do kind of a maximum likelihood estimate, in the sense that we'll find out will solve a optimization problem which will give us the value of this. So if we look at so what are the parameters in the Gaussian mixture model? If we call it as theta, it is the parameter set is pi1, pi2 up to pi k if we have k components, mu1, mu2 up to mu k if we have k components, and sigma 1, sigma 2, sigma k if we have k components. This is your pi. And we are interested in theta star, the optimal value of pi, such that we maximize over all possible values of theta the likelihood, or rather the log likelihood of the training data given a value of theta. Because you see here, the moment you assume a value of pi, mu, and sigma, you get a value of given a particular example. So if you fix your x to say x1 and this to x1, and if you know pi, mu, and sigma, this is a constant value. This is also a constant value, and add it up over all k, that is a constant value. So that gives the likelihood of x1. Similarly, we have x1 to xn. So the total likelihood if x1 to xn are independent are the product of these likelihoods. And if you take the logarithm, the log likelihood, the total log likelihood is sum I equal to 1 to n xi. It is the log likelihood. You take the product in the log, it becomes sum, and we want a theta star which will maximize this log likelihood. So we want a value of pi1, pi2, pi k, mu1, mu2, mu k, sigma 1, sigma 2, sigma k, which gives the, for all this n, capital N number of training data, the highest value of this one log likelihood. It's not an easy problem. It's a very complex optimization problem, and we will use a latent variable to obtain a quick solution to this optimization problem. Maybe not the optimal solution, but a quick solution to this optimization problem. Okay, so now let us introduce a latent variable. All right, so we said that your data, the distribution of the data is a mixture of k Gaussians, 3 Gaussians in this case. So we give a generative model for the data in the following manner. So what we do is first we generate an integer z, which takes on a value 1 to 3 or 1 to k. So we generate an integer between 1 to k. Okay. So this z is the latent, we call this integer as a latent variable z. This integer sometimes is called a responsibility. That means this integer decides that from which Gaussian among these 3 Gaussians we should generate the data. Okay. From which Gaussian? Let's say z is 2. So that means from this Gaussian we'll generate the data. So first we generate z, which is 1 or 2 or 3. And once we know the value of z, we have generated the value of z, we generate the actual 2-dimensional point from the second Gaussian, say z equal to 2. Say z equal to 2. Now we will generate x using the second Gaussian. So this is our data generation process. First we generate z 1 to 3, 1 or 2 or 3, and depending on the value of z, you use one of these 3 Gaussians to generate your x. This way you generate the data. Okay, this is our generative model. So it is 2 distributions. One is a Gaussian distribution, rather 4 distributions. One is a simple multinomial distribution generating numbers. It's like throwing a dice. It's 1 to k dice. You generate a number, and once that is generated, conditional on that, we use one of these 3 Gaussians. So Z is sometimes called a responsibility. Who generated this data? All right, so that's what we have said. And this 1 to z, z equal to 1 to 3, this I am not uniformly generating. This I am generating with probability pi1. I am generating probability 2. I am generating 2 with probability pi3. I am generating 3. Okay, so if pi1 is 0.1, the probability of generating 1 is 0.1, generating 2 is 0.2, pi2 is 0.2, and so on. And they have to add up to 1, otherwise Z will not be a probability distribution. Right. So let me take a typical example. Say pi1 is very large, pi2 is smaller, and pi3 is say, even smaller. So this pi1 will, let's say, take 0.8. This I will take say 0.15, and this I will take say 0.05. These are the pi1, pi2, and pi3 values. So naturally, you can see the Z will most likely be from the distribution 1. And once it is from distribution 1, I just generate according to this Gaussian. So the point will lie. So with a very high probability, the point will lie somewhere here. Okay, so that is what I have told. So Z is a categorical multinomial rather with pi. Z is the latent variable. Z is kind of not see, if you are just given a bunch of x's, you are not given what your cluster member or Gaussian component membership it is. That we are hypothesizing, we are assuming. Okay, so your Px, given this kind of latent model or latent generative model, can be thought of as first Pz equal to k with probability pi k, then x given z equal to k, the product of these two, which is a normal. So this is multinomial, this is normal, but this is normal according to mu k sigma k if z equal to k. So this is a product of these two distribution, and this not only you have to do for a single k, you have to do it for, you have to add it up over all k. You have to add it up over all k. Right? Because see, moment you generate a z, this pi, it is a multinomial. So it will be with k equal to 1 with pi 1, k equal to 2 with pi 2. So you have to add it over all k to get the distribution. All right, so if this is our generative model, so our log likelihood is like this. Remember, this is my generative model. Pz equal to k into Px given z equal to k. So this is our maximum likelihood expression given P of x, given pi, mu, and sigma, that is theta. The expression is assuming x1, you are given data points, you are given data points x1 to xn, which are independent. So the likelihood gets multiplied, the log likelihood gets added up over n equal to 1 to n, and this is the log likelihood for single xn. This is the log likelihood. So let me write this as x1, x2, s, and xn. This is the log likelihood for single xn, which is nothing but summation k equal to 1 to k, the mixer model, the definition of the mixer model, pi 1 n xn mu 1 sigma 1 added up for all k. Okay, this is our log likelihood. So this is actually the maximum log likelihood, which is same as log likelihood. So how do we optimize this? Note one thing: it's not an unconstant optimization problem. We have a constant that I equal to 1 to k pi I should be 1 in order for the entire thing to be a distribution. Right, so it's a constant optimization. Because see, pi, mu, sigma, these are the optimization variables, and you have a constant on them. This is a constant optimization problem. Okay, so this is the summary. This is our expression for the Gaussian mixture model, a generative model consisting of two parts, this part and this part. And then this is the one generative model, and from that you have the joint distribution, and this is your expression for the likelihood, which is this. Okay. Two things to be noted. First thing is that if you look at the expression for the log likelihood, there is a latent variable for every, there is a separate latent variable for every xi. Every xi has a latent variable zi, which is basically the which Gaussian component that xi belongs to. In fact, it's not exactly which Gaussian. It's a vector associated with every xi, denoting the probabilities of belonging to Gaussian 1, Gaussian 2, Gaussian 3, Gaussian k. Gaussian k. So this is the first problem. So there is a so note one thing I told earlier that see this mu sigma, these parameters hold for all x1 to xn, whereas the latent variable z is specific to a particular xi. Is specific to the cluster membership is specific. I am telling cluster membership, it is a vector, but it is easier to visualize a cluster membership. So the cluster membership is specific for every example. Depends on z depends on where x lies, and whereas mu sigma are constant. Okay, so now how do we estimate this? First, I am giving you an insight. Then you think. All right. So let me come to this picture. Okay. So suppose I knew the mu and sigma. So suppose I know the values of mu1, sigma 1, mu2, sigma 2, mu3, sigma 3. Suppose I knew the values. Then given a point xi, it is very easy to find zi. Suppose I know mu1, sigma 1, mu2, sigma 2, mu3. Then if I give you xi, you can easily find the latent variable zi. How? I'll just find for every xi, I'll find in xi mu1, sigma 1. I'll find in xi mu2, sigma 2. I'll find in xi mu3, sigma 3, and these values, they will directly give my z. Z I have told is a vector, so this will give me pi1, not pi1 actually. This will give me z1. This will give me z2. It will give me z3 for I. So this will rather give me the zi vector. The highest among them you can consider as the, but it's not, I mean, for reasons here, for example, the zeta is not a single value. It's with some probability it belongs to both the components. So if I know, the point to be noted, if I know mu1, sigma 1, mu2, sigma 2, mu3, sigma 3, I can easily find out z for a given point x. Observation 1. Observation 2. So if I'm writing it as vector, I'm not writing known. Easy to find zi. Similarly, if for a point xi, if zeta is known, it is easy to estimate mu and sigma. How? See what so I have a bunch of points x1, I have x2, I have xn, I have a set of points, and for every point I know what their z is. I know what their z is. Okay, so again, I mean, for ease of visualization, this Z is a vector, but I can assume Z to be belonging to which Gaussian it belongs. This X1 belongs to. Say X1 belongs to first Gaussian, X2 belongs to first Gaussian, also X3 belongs to second Gaussian, and so on. So how I'll estimate mu sigma if Z is known for all X1 to Xn? I will just collect all the X1 points. I'll collect all the X2 points, Z2 points. I'll collect all the Z2 points. From endpoints among the endpoints, I'll group endpoints into all belonging to Z equal to 1, all belonging to Z equal to 2, all belonging to Z equal to 3. This is not entirely correct. I will see that you can easily generalize it to the vector case. And once I have grouped them, I'll take their average and find mu1. I'll take their average and find mu2. I'll take their average and find mu3. And I'll take their covariance. Just covariance, you know, x minus mu, that from the matrix you can easily find given a set of points. I find sigma 1, I find sigma 2, I find sigma 3. So if Z is known for x1 to xn, it is easy to estimate mu1 sigma 1, mu2 sigma 2, mu3 sigma 3. So let me write down this. If Zi is known, easy to find mu sigma. Okay. Hello.
Sir, I have a couple of doubts here. Sir, first of all, like this Z is, if I'm not wrong, Z is the latent variable, right?
Yes.
So, sir, a few slides back you told that pi was a latent variable. Or sorry,
no, sorry. Pi is not the latent variable. Pi is a parameter. I'm mistaken. Pi is a parameter. Pi, mu, sigma are parameters.
Okay.
Very good point. So how do you estimate pi 1? I revised this. How do you estimate pi 1? You find out of total n points, how many belonging to 1, how many belonging to 2. That ratio would be pi 1, pi 2, pi 3. You have capital N points. You know what ratio is mu1, what ratio is mu2. That will give me. So that I estimate pi.
So, sir, pi is basically p of z equal to z1 or z equal to z2. Is it that?
Pi is a prior probability.
I mean, yeah, prior probability. Okay.
Prior probability. But so pi is the prior probability, whereas this is the likelihood probability.
Okay.
This is the likelihood probability. Okay. So sorry, yeah, very good point. I missed that.
And so, okay, so I understand the same doubt, but as pi is not pi is a parameter and it's not a latent variable. Yeah. Okay.
No, pi is a parameter. So
right.
Pi is the parameter, because see, the definition of the probability distribution is not just defined based on mu and sigma. It also needs pi. This is the expression for the distribution. It also needs pi. So this is a global variable. For any x you take, the pi value is same. Whereas this z vector is this, basically this vector. Z vector is this vector. And so zi, this is a local variable. Mu1 sigma 1 comma n xi mu2 sigma 2 and so on. This is the z vector. Okay, so Z basically given a point xi with what probability it belongs to component 1, with what probability it belongs to component 2, what probability it belongs to component 3. And pi is, if you randomly pick up a point prior without knowing what its value x is, what is the probability belongs to 1, 2, and 3.
Okay, good. So pi is common for all points.
Pi is a common for all the points, whereas Z is specific to a point.
Specific. Okay.
The Z depends on so if the Z if Z falls here, it has one. X falls here, Z has one value. If X falls here, Z has another value. If X falls here, Z has another value.
Yes. Okay. Got it.
Okay. So actually, I mean, I missed that, but it is all. But this still holds that if you know pi, mu, and sigma, you can easily find Z. So Z, I actually also revised this also. So Z is not actually Z is not this. Z is pi 1 times this.
Yeah.
Pi 2 times this and pi 3 times this. That is your Z. Prior on Z and into the likelihood. So the thing is that if you know pi mu sigma, it's easy to find Z for a point. If you know Z for all the points, it is easy to estimate pi mu and sigma. So it's kind of a circular thing. It's kind of a circular thing. So that is what I told that. In fact, I have just kind of said that pi mu and sigma is mu is sum of all the Z1 equal to 1 points, Z2 equal to 1 points. But so this intuitively I have told that mu1 is sum of all the Z1 points, but you can easily show that this is given the value of Z, that this points belongs to 1 with this probability, 2 with this probability. These are actually the maximum likelihood estimates of mu and sigma. These are actually the maximum likelihood estimates also. Right. So you know, if you are given a bunch of points x1 to xn, their average value is the maximum likelihood estimate of their mean. If their IID is the maximum likelihood estimate of their mean. That's what we did. But you need to actually show it also. So if this is your likelihood function, if you take the derivative with respect to mu and equate it to 0, you will actually get this same expressions, this intuitive expressions itself. So let me explain what is intuitive expression. This is for every point x, I know the Z values, the latent values. And then the likelihood, log likelihood rather, would be something like this. If you take derivative and equate to 0, then mu would be not one thing. So that's what I said. I collect all the points which belong to, which has Z equal to 1, divided, add up their x value divided by the total number of points for which Z equal to 1. And sigma is similarly x minus, once you have estimated mu, it is all the points with Z equal to 1, x minus mu1, x minus mu2 transpose divided by this. And pi is the ratio of the number of points with respect to capital N, which belongs to component 1. This is mu k, sigma k, zk. Okay. So what we do, remember these two facts, that if we know Z, you find mu. If you know mu, you find Z. So these two are combined to give a very nice iterative optimization algorithm called the expectation-maximization algorithm. All right. So what we do in the so this has two steps known as the E step or the expectation step, and M step, the maximization step. So what we do in the E step is the following. It's like this. So in the E step, what we do? Yes. In the E step, what we do? Assume Z is Zi is known. Sorry, assume pi, mu, and sigma are known. Assume pi, mu, and sigma are known in the E step. Then, given a point x, I compute the probability of belonging to Gaussian 1, Gaussian 2, Gaussian 3. So assuming pi, fix your pi, mu, and sigma, and find out the pxi z equal to 1, pxi z equal to 2, pxi z equal to 3. So you find pxi given z equal to 1, pxi given z equal to 2, and so on. You find these probabilities, fixing your mu and sigma. That is what we call the E step. So this gives you values of z. This gives you the z vector. This gives you the z vector. In the next step, assuming the z vector, you find out z given, you estimate mu and sigma and pi by this formula. Okay, so that is your M step. And repeat this over iterations. Okay, you repeat this over iterations. So what we do is the following. So all right, one thing we forgot to mention is that you have to initialize pi, mu, and sigma to some random values or initial values. Okay, then iteratively follow the E step, then the M step, first the E step, then the M step, till convergence is achieved. That means mu, pi, sigma do not change over successive iterations. Okay, so these things are very easy. So first in each step, what you do, you assume mu, pi, sigma is known. For every x in the training set, you estimate the z vector, probability of Gaussian 1, probability of Gaussian 2, probability of Gaussian 3. And in the second step, once these probabilities are known, you follow the M step. That means given these probabilities, assume estimate the values of pi, mu, sigma. The first one you can see is if you know pi, mu, sigma, you get the full distribution on Z. So you are not making a point estimate on Z. This is a Bayesian estimate of Z. Bayesian estimate of Z, because I know the full distribution of Z. Z is a vector. I know the full vector, not a single point. I know the full vector of Z distribution values, probability values. So it is a three-dimensional vector in this case, 0.9 to component 1, 0.1 to component 2, and so on. So this is a full Bayesian estimate, whereas the M step gives a single value of pi, mu, and sigma. So this is a point estimate. Is a point estimate. Is actually the MLE estimate. Because these equations, if you remember, I have take the derivative of the log likelihood, set it to 0, and got those expressions. Again, I'm not doing it. It is very easy actually. If you plug in the equation for Gaussian, you will get it. So, so as I have said, that this is a hybrid inference. For the latent variable, we are doing the full posterior, whereas for the parameters, we are doing the MLE, point estimate. So this is, and this simplifies things. This nice iterative method in practice, in very few iterations, it converges. Okay, so these steps have not worked out. So this you can do. So this is the z vector that I talked about, lambda k, z equal to k given x. You can, assuming mu, sigma, and pi, this is the expression. Again, this is setting the log likelihood derivative to 0. And in the M step, again, if you do it, and if you do all those things, you can, this is just the mu k, sigma k, pi k estimate that we wrote down. That also for a vector case, it will just look like this. A simple, this actually means the simple estimate. Okay, so this gives this is a derivation of the expression I get by setting derivative of log likelihood to 0. Okay. All right, so this is the summary. You initialize mean mu k, covariance sigma k, and mixing coefficient pi k. Estimate, so this lambda k is the zk vector. So this gives zk given x. So this is lambda 1 is the first component of zi, lambda 2 second component, and so on. This is how you estimate them. Note that here value of mu, sigma, pi are fixed in the step. This is how you get your z vector. Once you have got your z vector, you in the m step you re-estimate. You use this gamma value. You use this gamma value, that is the components of the z vector value in this way. So I make a small change. In the earlier explanation, I gave that if z belongs to component 1, I generalize it. Instead of hard belongingness to component 1, this is the soft belongingness, soft membership to component 1, gamma k. So you weight xn by this soft belongingness, add up over all n, you get mu k. The first component. Second component, you get mu1 is the first component, lambda 1, sorry, gamma 1 if you add. Mu2 you get by adding gamma 2 and so on. Similarly, you use this for sigma k. So just and for pi k. So you just check these two steps, and after every iteration, you check the value of log likelihood. If it converges, you stop. So this is the EM algorithm. So I have explained it for only the Gaussian mixture model. In fact, this is a much more powerful algorithm. This can be used for any hybrid inferencing procedure. The fundamental principle is that the latent each step estimates the latent variables. Full posterior estimates the latent variable. The M step is a point estimate of the global parameters. So here the local, because see gamma k is local, it is specific to x, which location of x will determine what is belongingness to cluster 1, cluster 2, cluster 3. So this is the full posterior estimate of the local latent variables, and M is a point estimate of the global parameter variables. So we use both. This is a hybrid inference. This is a much powerful technique. It is used not only in GMM, but many other such hybrid inferencing or hybrid optimization, like maximum likelihood procedure also. We will in the next class we'll do a full generalized EM for any distribution, any such problem. Okay, so thank you. I will stop here, and if you have any queries, two announcements. I have uploaded some practice problems which you can practice, and I have also okay, I have also uploaded the assignments. You can look into it. So Saturday we are having a test.